I'll talk about a practical implementation of clustered fault-tolerant write acceleration in a virtualized environment. So as more and more applications get virtualized, VM density increases in a virtualized data center, and data centers experience what is commonly referred to as an I/O bottleneck. The cumulative I/O, because of all the cumulative I/O of the VMs as they go up. So there are several ways to solve this problem. One of them is to provision better or more hardware. However, buying more hardware to solve the performance problem is not the right thing, because you're buying capacity to solve performance. And usually such a change where you're buying better hardware is a disruptive change. You need to have a plan for system downtime. Also, this is usually a temporary fix in that whatever hardware you have, the faster SAN is pretty much very soon going to reach its peak capacity as well. So enter Hostsite Flash. This is a non-disruptive change. On the host, you install a flash device, and you use the flash device to cache an application's working set. So by bringing the working set close to the beginning of, or getting it to the beginning of the application's I/O, you accelerate the I/O, which is the key idea. So Hostsite Flash has been used for accelerating I/Os before. One of the techniques is called as write-through, where only reads, where the Hostsite Flash is used to cache reads. So virtual machine reads are first issued to the Hostsite Flash. If there is a cache hit, then the read is serviced from the flash, and the VM sees flash latencies. If it's a cache miss, then the read is issued to the SAN. The data is then serviced by the SAN, and the host caches the read onto its own flash. And that is called write-through. You can also accelerate reads and writes, and a technique called write-back, in which reads are accelerated as they are in write-through, but every write is issued to the flash and is acknowledged back to the virtual machine on flash completion. So the VM experiences flash latencies. In the background, the dirty VM writes are then issued to the SAN. This is a technique called write-back. So are there any benefits? The graph here on the y-axis plots the cumulative throughput of two virtual machines, one running Microsoft JetStress, the other being FIO. It's a mixture of reads and writes, and running in write-through versus write-back. And we can see that the throughput with write-back is clearly much better than what you get in write-through. And so there is benefits, but there are challenges when you want to use Hostsite Flash in write-back acceleration in virtualized environments. The first challenge here is that you need to preserve VM mobility. In order for better resource management, for load balancing, and for high availability, virtual machines are migrated between hosts in virtualized data centers. And the new host, when a virtual machine is migrated to the new host needs to be able to access the virtual machine's data. Data centers usually accomplish this by consolidating shared storage under all this storage under a shared SAN. However, if you bring in Hostsite Flash is a local resource, which means that when a virtual machine migrates from host 1 to host 2, if it had any dirty writes on the previous Hostsite Flash, it is now going to lose access to it. So virtual machine mobility needs to be preserved in the presence of Hostsite Flash when you're using it to accelerate writes. The second challenge is sustained writes. If you have virtual machines that are very write intensive, then they can fill up the flash space that they have, and then they need to be stalled. They cannot be allowed to write to SAN after that, because the SAN has stale data, and writing to SAN would cause data corruption. The next challenge is fault tolerance. In case of a flash failure, if a virtual machine has dirty writes on its flash, then there is going to be data loss. So our contributions, we introduce FVP. FVP solves these three challenges. I will talk about how FVP instruments seamless virtual machine migration when you have Hostsite Flash for accelerating writes. We introduce a concept called flow control, which will gracefully handles sustained writes. And I will also talk about how we introduce fault tolerance. The key idea being that we replicate VM writes onto other Hostsite Flash, so you can now be flash fault tolerant. Just a quick recap of the acceleration policies. I talked about write through, write back, and then FVP introduces another policy, write back with peers. In this policy, every VM write is replicated to peer hosts, Hostsite Flash. So writes, then when a VM issues a write, the write is issued to its own Hostsite Flash as well as transmitted to a peer. The peer also writes that write onto its own Hostsite Flash. So VM writes experience a higher latency because you also have to transmit the write to the peer. So as a VM writes accumulate on its Hostsite Flash, those writes need to be periodically issued to the SAN, and that is done by a process called the Dstager. So each write, when it at ingest point, is marked with a monotonically increasing serial number. Writes get batched, as in every batch, no two writes in a batch overlap. And all the writes in a batch are concurrently issued by the SAN. So that is a function of the Dstager. When all the writes complete or are acknowledged by the SAN, then the Dstager issues what is called as a checkpoint, and the checkpoint gets persisted onto the flash. In order to allow for fair sharing of the SAN's bandwidth, the Dstager cycles through write batches for every VM in a round-robin fashion. So what is a checkpoint? The main objective of a checkpoint is to allow hosts to evict dirty writes or to evict writes from their flash that have already been acknowledged by the SAN. So a checkpoint consists of the serial number and the VM's UUID. If there are any peers that have been allocated for a VM, then a checkpoint is also transmitted to the peers. The peer also commits or persists its checkpoint on its own Hostsite Flash. So once the serial number is there, the primary and the peer hosts are now free to evict those writes that have already been acknowledged by SAN, and those are the writes whose serial number is less than the latest checkpoint. Checkpoints reduce recovery time, and I'll talk about that when we discuss fault tolerance. So our first contribution, how FVP instruments seamless virtual machine migration. So the way we do that is that every host has access to every other host's Hostsite Flash. Also, FVP keeps state. So when a VM migrates from one host to the second host, let's say it migrates from host 1 to host 2, host 2 knows that the previous host for that particular virtual machine was host 1. So when that VM issues a read on host 2 that causes a cache miss, host 2 retransmits that read to the previous host. The previous host services the read from its own Hostsite Flash, transmits the read back to host 2. Host 2 caches that read on its own Hostsite Flash and services the read to the VM. So basically what host 2 does is it eventually rebuilds the VM's footprint on its own local flash. Eventually, either after a certain amount of time or when the cache misses go down, the second host stops issuing remote reads to the previous host. Seamless VM migration is thus instrumented. The second contribution is flow control. The problem we are trying to solve here is that if you have a very write-intensive VM, then it's going to fill up its flash space before the Dstager has time to flush those writes to SAN and make more space for new writes to come in. This could also happen if the SAN is slow or has been overloaded and therefore is not being able to service the writes. In any case, if this happens, then the VM needs to be stalled. And by that I mean that the VM cannot be permitted to issue any more I/O. And that is because until its dirty writes have been persisted to SAN, it cannot be allowed to write to SAN to avoid data corruption. So it is possible that the Dstager evicts is able to flush some writes, and so there's a little space now that has been made on the flash, and so the VM can be unstalled. But if the SAN is still loaded or the VM is still writing intensively, then the VM has to be stalled once again. And so the VM would suffer degraded performance, which is something that is unacceptable. So in order to solve this, FVP instruments flow control. So the key idea of flow control is that you need to slow down VMs that are going through these sustained write phases. To do this, FEP injects artificial delays when acknowledging a write to a VM, thereby slowing down the VM. This gives the Dstager some time to catch up and make more space for the VMs. FEP continues to introduce increasing amounts of delay to a point where in the worst condition, the VM will operate at SAN speed, which it would have done if there were no FEP. But the key point here is that the VM does not need to stall. It can continue at SAN speed until it is done with its intensive writes. So in order to trigger flow control, FEP uses some heuristics, and all the heuristics together indicate how long it is going to take the Dstager to create space or to flush the accumulated writes on SAN. There are a lot of details about this in our paper, so you could look at that. So most applications are bursty in that they are write intensive for short periods of time, and they don't have sustained write bursts. And short write bursts are very gracefully handled by the Flash. So the third challenge was fault tolerance, and I talked about the problem with what happens if there's a flash failure, and that is solved by replicating writes onto other hosts' flashes. But there are other scenarios that we also need to consider in a virtualized data center. For instance, in the case of a failure, the first thing is that the SAN is inconsistent state with respect to the VM. The SAN has stale data. Dirty VM writes have not been destaged to SAN. Now, if there is a host failure, some VMs might get, the affected VMs may migrate to another host to ensure high availability. If that host allows the VMs to issue writes, then data corruption might occur because the VM actually has dirty writes on its previous host that have not yet been destaged. So we have to solve for this as well. The way FEP prevents this from happening is that it uses on-disk locks. The ownership, so there is a lock persisted on the disk for every VM, and the lock is actually persisted on the VM's data store. The ownership of this lock is arbitrated by the virtual machine file system, in that only one host can acquire a lock for that VM, and that is the host that is eligible to issue IOs on behalf of the VM. So the lock contents are essentially the checkpoint, which we talked about before, which is this last serial number of the write that was acknowledged from the SAN, and the VM's acceleration policy, whether it was in write back or write back peer, etc. A copy of a lock file is also, a read-only copy is also kept, and I'll talk about that when we discuss some fault tolerant scenarios. So I will be discussing flash failures and host failures. Then for network failures and SAN failures, you can look at our paper. So in the interest of time, I'll just cover 2 failure modes right now. So in the case of a flash failure, the host that experiences the flash failure relinquishes the lock. If there are any VMs that are in write-through, well, they are not affected. There is no data loss. They didn't have any dirty data on the flash to begin with. If there are VMs in write-back, as I discussed before, there will be the recovery is not possible. There will be data loss, and those VMs will be stalled. If there were any VMs whose writes had been replicated to peers, recovery is instrumented through a process called online replay. The peers periodically attempt to acquire the on-disk lock for the VMs whose writes they are replicating. So since the primary host whose flash has failed has relinquished the lock, one of the peer acquires the lock, and the ownership is again arbitrated by the virtual machine file system. So the peer that succeeds destages its replicated writes from its host flash for the affected VM onto SAN. And once it is done, it releases the lock. So the VM's dirty data is now on SAN. If, meanwhile, for high availability, the affected VMs have migrated to other hosts, then the new host could acquire the lock. Once it acquires the lock, it can now look at the lock contents, and from the lock contents, it's find that the VM was in write back on the previous host, and which indicates to it that the VM had dirty data, still has pending dirty data on the previous host. So it relinquishes the lock. Then one of the peers and then it stalls the VM after it relinquishes the lock, and it periodically polls the read-only copy to wait for when the dirty data has been flushed or has been synced to SAN. So this is how flash failure would get handled. Next, in the case of host failure. In the case of host failure, again, the virtual machine file system will release a lock as part of failure detection. For VMs in write-through, again, there is no data loss. For VMs in write-back, recovery is instrumented via a process called offline replay. When the failed host recovers, it scans its flash device, looking for all the dirty writes for those affected VMs, and then it will replay or flush those writes to SAN. Once it has done that, it will uninstall the VMs if they have already come up online, and then the VMs can go on from there on. If there are any VMs whose writes had been peered, who write back in peer, recovery can be attempted by their peers in online replay, via online replay, as I discussed previously. If any VMs have migrated, then again, the new host, like I discussed in the previous case, would stall the VM until their data has been persisted to SAN. So the key takeaways here are, I talked about how checkpoints speed up recovery. And checkpoints are persisted regularly by the host that is performing the recovery in order to speed up cascading failures. So if, let's say, a host goes down and then a peer takes over the recovery, if the peer goes down, another peer takes over. So the second peer can now take over from where the first peer left off. FVP can recover from up to P flash failures. So if you have just one flash, also in the case that, let's say, all P+1 hosts have gone down, you can take the one flash that is still fine, you can take it and install it in another host that still has access to the VM's data store, and recovery can still be complete. So it can recover from multiple host failures. Recovery is distributed in that every peer or every host is self-sufficient. It has all the information it needs in order to execute the recovery for the affected VM. Once it has a lock, it knows how to proceed. It does not need to communicate with other hosts to figure out how to go forward. So I'll discuss some experimental evaluation. I'll talk about how VM migration is instrumented, how flow control is triggered. We'll talk about fault tolerance, the cost versus benefits. I will not be discussing right now how FVP absorbs short write bursts, but the details are in our paper. So here, the graph is showing the average read latency experienced by a virtual machine as it migrates from host 1 to host 2. So the VM, while it was on host 1, we ran a read workload, which was generating random 4K reads using iometer. So it was a random workload, and as more and more cache hits started happening, the read latency reduced. Eventually, the entire application's working set was now brought in, had been cached on the flash, and so now you have 100% cache hits, and the VM read latencies are basically experiencing flash latencies. The VM then migrates, and after it migrates, host 2, until it has rebuilt the flash, starts issuing remote reads to the previous host. So as we can see that as it had more and more cache hits, the read latency started reducing until, again, it had rebuilt the VM's footprint on its own host site flash, and now all the reads on the host 2 also see flash latencies. The key point here to note is that the VM, when it was on host 2, it took a much shorter time for the application working set to be cached than it took when the data was coming in from the SAN, because when it had migrated, the reads were getting serviced from the previous host, and it only incurred network and flash latencies. So this is how VM migration is preserved. The next we talk about how flow control triggers and how it works. So in order to do this, we have a write workload. We have a VM that is issuing sustained writes. So VM issues writes to flash, and the VM sees flash latencies because it is acknowledged once Flash is absorbed the write. Once the writes that are on Flash are then grouped or batched by the Dstager, and the Dstager is then issuing them to SAN. So the Dstager experiences SAN latencies. So the two graphs here, on the top graph, that graph on the top is plotting the rate at which the writes were acknowledged back to the VM, and the rate at which the writes were acknowledged to the Dstager. So the Dstager experiences, like I said, SAN latencies. And the graph at the bottom is showing you the write latency observed by the VM. So as the VM is issuing writes for the first 80 seconds, it is seeing flash latencies because the flash is able to absorb all those writes. But after 80 seconds, the flash space fills up, and FEP triggers flow control. Once flow control comes into place, it starts injecting additional delays when acknowledging the writes to the VM. And that's what we see in graph 2, that the VM is now experiencing much higher latencies than it was when the flash was not full. So the writes are now acknowledged at a slower rate at SAN, and at the rate at which SAN can absorb the writes. After the write burst is over, the VM is functioning is now slower. The Dstager, however, continues to continues to flush the writes to SAN. So by the time the next write burst comes in, again, the VM sees flash latencies until again it might hit flow control. The key takeaway here is that there is no need to stall the VM. The VM was not stalled. At worst, the VM experienced SAN latencies. It did not need to be stalled. So that's what flow control brings in. So fault tolerance. So in order to look at what are the cost versus benefits of achieving fault tolerance, this graph plots the throughput of the cumulative throughput of two VMs when they were configured in write through, in write back, and when they were using 1 and 2 peers. So as you can see, the throughput that the black line here is plotting the throughput of the cumulative throughput when they were in write back, when there was no peering in place. Then the next one, the graph is showing what happens when there is 1 peer, and then when there were 2 peers. So when peering is in works, every write incurs an additional latency, the network latency, because you have to transmit the write to another peer. And because of that, your throughput reduces. This is what we are seeing when you're peering. When 2 peers were used, we see that the throughput went reduced even beyond when 1 peer was used. And that's because right now, FEP does not instrument support for multiple NICs. When we do that, then the write latency would track the latency of the slowest network, and then we wouldn't see a difference in throughput whether you used 1 peer or multiple peers. The key takeaway here is that fault tolerance involves a trade-off, and the trade-off is higher write latencies or reduced throughput. But then from the graph, we can see that even if you did use peering, throughput reduced, but it was actually even better. Even then, it was better than write through. So with peering, you got fault tolerance and you got write acceleration. So this is a win-win situation. So I discussed what are the main contributions of FEP. In future, there's plenty of work to do, but essentially we're trying to build more intelligence or adaptability into FEP, looking at VM workloads, and then adapting according to that. So that's it. I can take any questions if you have them.
Saurabh Kadekodi, CM. So can you please go back to your VM migration graph?
Graph?
Yeah. So there you showed that the latency was less when you were migrating because you took it from the other host that had cached it.
Yes, that's correct.
I'm just wondering how busy was host 1 here? Because usually the VM would migrate because of high availability, in which case the flash that was used for caching the reads for the VM that was migrated would be reused very quickly, and then you'll have to go back to SAN to get.
So virtual machines don't migrate only for high availability. They might migrate for just power management. They could migrate for many other reasons. Okay. In this particular case, the objective of this graph is to show that those latencies will still be lower latencies than what you would see if you were to issue the read to the SAN.
Okay.
And that is the key idea here.
And secondly, if you were to issue reads, you said that if the reads would be targeted to the host that had them, and suppose with a write back with peer, would they be going to each of the peers before going to SAN, or?
The reads?
Yeah.
No, they wouldn't. They would only go back to one host.
One host and
yes.
Okay.
Yeah.
Thanks.
We have time for one more quick question.
Okay, so I'm Mahesh from Nimble Storage. It seems that this work is focused on removing the deficiencies of write-back caching relative to write-through caching. In my mind, the bigger question is why does write-back caching have a benefit over write-through caching? And especially when peering is involved, so the data needs to be mirrored over the network anyway. And I know that you showed some graphs, but just fundamentally, why is it that, given that the data needs to be sent over the network, write-back caching still has an advantage compared to write-through?
Because write-back caching is advantageous because essentially most virtual machines are bursty. And during the burst period, the flash is able to very quickly absorb the burst. And at that time, the VM will see very quick acceleration of I/O, instead of sending those over to the network. So those VMs will be the best. Also the VMs, so did I answer your question?
Well, even that burst needs to be mirrored, so it still needs to go over the network.
The burst needs to be mirrored, but network latencies are much lower than SAN latencies. And therefore, that mirroring, actually like we saw in the graph, even though you mirror, the throughput is much better than you would for a write-through.
I guess it depends on the SAN you're using.
Of course, yes. It depends on the network you're using. It depends on lots of things. So, yes. It would depend on the SAN, yeah.
Okay, I'll
Yeah,
chat
we
with
should
you
definitely
later.
talk later.
Thank you.
Thanks.